Welcome to The Explainer. Today, we're diving deep into a problem that if you use Kubernetes, you are going to hit sooner or later, the dreaded OOMKilled error. It's one of those cryptic messages that can really ruin your day. But don't worry, we're going to walk through exactly how to handle it, from that first frantic alert all the way to the permanent fix. So here's our game plan. We're going to treat this like a real-life incident. First, we'll set the scene for the crisis. Then, we'll grab our detective hats and run some initial triage commands. After that, we'll apply some first aid to stabilize the system. With some breathing room, we can do a deeper dive to find the root cause, figure out the real fix for our code and config, and wrap it all up with some best practices so, this doesn't happen again. All right, let's set the scene. Imagine this. It's your on-call shift. Everything's quiet. And then, bam, the pager goes off. Your service is on fire. Yeah, you're seeing 5xx errors everywhere, your pods are stuck in this awful restart loop, and the pressure is on. You've got to figure out what's happening, and you've got to do it fast. A lot of the time, the culprit is something sneaky, like a memory leak, and that leads to this. OOMKilled. It's short for out-of-memory killed. It basically means Kubernetes is stepping in and killing your containers because they're using way more memory than they were told they could. It's the cluster protecting itself, but for you, it means your application is down, hard. Okay, so the service is down and we've got a prime suspect, a memory leak. It's time to put on our detective hats and gather some actual evidence. These three commands are your best friends in this situation. Think of them as your detective's toolkit. kubectl get events gives you the high-level neighborhood watch report, confirming, yep, there's been some killing going on. Then, describe pod lets you zoom in on a specific pod and get the cause of death. That's where you'll see stuff like exit code 137. And finally, top pod is like creating a police lineup of all your pods sorted by memory usage so you can point right at the one causing all the trouble. Okay, we've got our evidence, but before we go any further, we need to stop the bleeding. The absolute #1 priority is to get the service stable again. And here's the 3-step first aid plan to do just that. First, you scale out, add more replicas to spread the load. Second, you give the pods a bit more breathing room, a bigger memory limit. And third, you restart the whole deployment to flush out any memory that's already been leaked. Now, let's be clear. This isn't the cure. This is the tourniquet that buys you time to find the cure. Okay, the fire is contained, for now. With the system stabilized, we've finally got some breathing room to do the real detective work and find the source of this leak. When you dig into that pod description, you find the smoking gun. This single line tells you everything. The reason is explicitly OOMKilled. And that exit code 137, that's not just some random number. It's the system's specific signal for I was killed by an external signal, which in this context almost always means it was killed for using too much memory. And that high restart count, that tells you this isn't a fluke, it's a chronic problem. And we can get even more granular. You can actually go inside the container's control group, or C group, which is just the fancy Linux thing that isolates resources, and see the exact memory limit Kubernetes is enforcing, right down to the byte. And that number? That's your 512 megabytes. And then, for the really cool part, you can check another file right next to it and watch the actual memory usage climb in real time. Seeing that number creep up and get dangerously close to the limit is all the proof you need. You're watching a memory leak happen right before your eyes. So, we've confirmed it, it's a leak. Now for the most important part, the permanent cure. And this isn't just one thing, it's a two-pronged attack. We have to fix the application code and our Kubernetes configuration. This is a perfect, if simple, example of the problem. On the left, you've got this tiny bit of Python code that will just keep adding stuff to a list forever. It will never stop. It will eat all the memory you give it. The fix isn't just to throw more memory at it. The real fix, the principle on the right, is to put a boundary on it in the code itself. Use a cache that has a maximum size, or some way to kick out old data. You have to tell your app when to stop. The other half of this puzzle is right in your Kubernetes YAML file. And this part is absolutely non-negotiable. You have to set memory requests and limits. The request tells Kubernetes the minimum your pod needs to even get started. The limit is the hard ceiling. It's the kill switch that prevents one leaky pod from crashing the whole server. It's a critical part of the deal you make with the cluster. Look, fixing the immediate problem is great. We put out the fire, but preventing the next fire, that's where we become truly great engineers. So let's boil it all down to the key takeaways. First, always set those memory requests and limits. Second, remember that things like autoscaling are great for handling real traffic spikes, but they will not save you from a memory leak. You also need good monitoring. You have to be able to see your app's memory usage. In your code, think about using bounded data structures. And finally, test your fixes in staging and watch them closely for a day or two after you deploy. These habits are what build truly resilient systems. At the end of the day, this whole incident response drill really shines a light on the importance of proactive monitoring. You reacted, you fixed it, and that's awesome. But the real question to ask yourself now is, what can you do to improve your observability so that next time you catch an issue like this before it ever impacts a single user? That's the real challenge, isn't it?